and they cost between $600 and $800 a piece and 4 of them. So our budget does not allow for us to purchase two more. Okay. So I think that's where we're at, and that. All right, so the first one is video clip, and we're gonna take these notes and we're gonna practice. You're gonna okay with that? That's all right. Okay. All right, here we go.
In chemistry, what's the worst that can happen? In most classes, the worst that can happen is just abject total failure. Just like failing a test, failing a class, having to rethink your life choices, maybe even quit, drop out of school, get a job at a diner, and start smoking Lucky Strikes. But in chemistry, the worst thing that can happen is death. And I don't want to make light of this. Labs are dangerous places. Chemists die younger than the average person, both because of workplace accidents and cancer caused by exposure to chemicals. But chemists have also done more to increase the average lifespan of humans on Earth than, in my opinion, any other profession. So it's a necessary hazard. Last week we talked about stuff mixing together, and that's important for sure. But today and for the next few weeks, we're going to talk about the actual reactions happening in those solutions. Dangerous reactions, atoms reorganizing themselves to create whole new substances. These are the processes that make our world the world that we know and love. Some of them are benign and beautiful, some of them are face-meltingly terrifying. And that's not hyperbole, I mean actual melted faces. Captain John Mullen, there. He blazed the first wagon trail across the Rocky Mountains into the interior of the Pacific Northwest. The captain's only been standing in this spot right here for about 75 years. And look what happened to his face. I know this maybe isn't the face melting you were expecting, but we're not so gruesome here at Crash Course Chemistry. The sorry state of Mr. Mullen's face here is the result of an acid-base reaction, one of the three major types of reactions that happen in solution that we'll be talking about here at Crash Course Chemistry. And the acid that did this was mostly sulfuric acid. I may be wondering who's been coming by and throwing sulfuric acid on statues. Well, actually, what they're doing the throwing is clouds, the sky, though the actual source of the sulfuric acid, that's 400 miles away at the Colstrip Power Plant in Colstrip, Montana, and also at coal-fired power plants all over the United States. The United States of America burns about 1 billion tons of coal per year, and most of that coal is mined right here in the U.S. Montana, where I live, is home to the Powder River Basin, a geographical location responsible for 40% of America's coal output. Between 50 and 70 freight trains ship out of the Powder River Basin every day. Each train has at least 115 coal cars and is more than 1.5 miles long. And all of this coal burning, it has effects, significant effects, acidic effects. But first, what exactly are acids and bases? Well, acids, sour. So sour, that's the first thing that we learned about acids, actually, and that's why acid actually means sour in Greek or Latin. And acids are excellent at dissolving stuff. They kill things and melt your face. What about bases? You might have some idea of what a base is. Bitter, tasting, slippery, like soap. Soap is, in fact, a base. And bases, like acids, are totally dangerous and can melt off your face. They're also like the anti-acid, basically. In fact, they're antacids. If you mix acids and bases together, they neutralize each other. But as with most things in chemistry and in life, when it comes right down to trying to define exactly what something is, it gets weird and messy and confusing and terrible. So, forget everything you ever learned about acids. Wipe the slate clean. The most common acid on Earth is water. And water is also the most common base. And am I saying this purely to confuse you? Yes. Well, mostly to convince you that the world is way more complicated than you thought it was. In 1923, two guys simultaneously defined acids and bases in the exact same way. Bronsted and Lowry defined them. They didn't classify them by how they acted or what they tasted like or even what they were made of. They defined them. And this was an impressive feat because a huge class of molecules, to some extent or another, act as acids and bases. So they come up with a definition that fit all of them, that was not so simple. Ronstadt and Lowry defined an acid as being anything that donates a proton and a base as being anything that accepts a proton. And when we say proton, what we're talking about here is a hydrogen atom without its electron. Usually this is happening in water. Acids and bases can react in a gas, but almost always they're in an aqueous solution. And when a proton gets donated in water, it is accepted by water. And H2O is converted into H3O+, a hydronium ion. So when an acid is added to water, it dissociates, like any other ionic compound, forming H3O+ and a negative ion. The acid has donated a proton to the water. Also, a little chemistry terminology thing, we usually just write H+ or say protons in solution, when in fact we are referring to hydronium ions. It's just a shorthand. In reality, H+ in aqueous solutions is always H3O+. Let's take a look at the dissociation of hydrochloric acid for some more terminology bits here. You see right off the bat that the HCl is donating a proton. But with many acids, particularly weaker acids, the reaction can actually go back the other way, with H3O+ donating its proton. So in this situation, every chemical in the reaction, also sometimes called the major species, can be called an acid or a base. On the left-hand side, the water is accepting the proton, so it's the base, and HCl is donating it, so it's the acid. And on the left-hand side, the Cl- would be accepting the proton, so that would be the conjugate base, and the hydronium ion is the conjugate acid. The phrase conjugate acid always used to confuse me because I thought it had something to do with conjugating verbs. It's actually the older original sense of the word, the one where conjugal or marriage-related visits for prisoners come from, which means joined together. For every acid, there is a conjugate base, and for every base, there is a conjugate acid. Previous definitions of acids and bases, particularly the one proposed by our old friend Arrhenius, relied on specific major species, most notably our friend the OH, or hydroxide ion. While hydroxide is in most bases, it's not in all of them. For example, ammonia acts as a base when it reacts with hydrochloric acid to form ammonium chloride. There's no hydroxide, but there's definitely proton donation and acceptance going on. Now, acids and bases are not all created equal. Certain acids really like to get rid of their protons and will only reluctantly convert back to their conjugate base by accepting the proton. We call them strong acids, and the conjugate base is a weak base. The same can be said for strong bases, and they're weak conjugate acids. The reason why all of the most interesting acid-base chemistry happens in water is that dihydrogen oxide is really great at being either a base accepting a proton from an acid or an acid donating a proton to a base. Thus, water is the world's most common acid and also the most common base. So, what does any of this have to do with power plants in John Mullen's face? When coal is burned, the sulfur in it reacts with oxygen to form sulfur dioxide. That sulfur dioxide then reacts with water and oxygen in the air to form sulfuric acid. When that sulfuric acid rains down, a set of acid-base reactions take place that damages limestone and metal and acidifies the water supply, making life harder for fish, coral, salamanders, and pretty much everything else. Limestone is mostly made of a chemical called calcium carbonate. The carbonate acts as the base, accepting sulfuric acid's protons and converting into carbonic acid, the conjugate acid, which breaks down into CO2 and water. Calcium and sulfate ions may precipitate as a salt, that's more commonly known as gypsum. Okay, the average ton of coal burned in America is about 3% sulfur. Supposing 100% of those 30 kilograms of sulfur leaves the smokestack and converts to sulfuric acid, how much limestone could that completely wash away? As I've said before, just follow the units. 30 kilograms of sulfur multiplied by 1,000 grams per kilogram, multiply that by 1 mole over 32.1 grams of sulfur to get 935 moles of sulfur in every ton of coal burned. Now, if every mole of that sulfur is converted to H2SO4 and every mole of that sulfuric acid reacts with a mole of limestone, converting it to a mole of gypsum, then that's 935 moles of limestone dissolved. There are 100.1 grams of calcium carbonate per mole. If we multiply that by 935 moles, we get 93,600 grams, or 93.6 kilograms. So each ton of coal burnt by a U.S. power plant produces enough sulfuric acid to dissolve about 94 kilograms of limestone. And as we burn about 1 billion tons of coal per year, it's safe to say that no statue is safe, except for one built of materials immune to acid, particularly oxidized copper, which will last pretty much forever, hence Lady Liberty's hand presiding over the Planet of the Apes. So, this is clearly a problem, I mean, not just for statues, but acid rain has killed or harmed huge swaths of forests. At the peak of acid rain problems in the U.S., the highest recorded acidity was around that of lemon juice, which I can tell you is pretty acidic, high enough to irritate human skin. This first became an issue for power generation when the British House of Lords in 1929 ruled that a power station was liable to damages caused to nearby crops by acid rain. So something had to be done. But what? Well, we already know one very common chemical that reacts easily with sulfuric acid, good old limestone. And in England, there is lots of limestone. By passing the smokestack gases through a limestone slurry, the SO2 converts to an acid and then reacts with the limestone, forming CaSO3, calcium sulfate. Now we're going to do something a little different for those of you who want to go the extra mile. Assuming that 1 billion metric tons of 3% sulfur coal is burned in America every year, and all of it is converted to SO2, how many tons of limestone would we need to scrub out 100% of that sulfur? Answers down below in the comments. The limestone scrubber is a good system, but it's not perfect. Many other flue gas desulfurization systems have been developed, and now through a combination of good policy, good science, and hard work, about 95% of sulfur-producing coal-fired power plants in the U.S. is removed before it leaves the smokestack. And through some even smarter chemistry, some of that SO2 is actually converted to industrially useful chemicals, for example, pure sulfuric acid, which is used in paper mills, iron and steel making, industrial cleaners, and chemical synthesis. Chemistry! Causing problems, but also fixing them. Thank you for watching this episode of Crash Course Chemistry. If you were paying attention, you may have learned that chemistry can cause death, that acids and bases are more complicated than you thought they were, and that an acid donates protons while a base accepts them. You also should have learned that when an acid donates a proton, it forms a conjugate base, and when a base donates a proton, it forms a conjugate acid. Also, we did a little bit of acid-base stoichiometry. This episode of Crash Course Chemistry was written by King Krieger and myself. The script was edited by Blakeney Pastino and our chemistry consultant. All right, so you're studying chemistry. What?
Nope. I just gotta write the next class. The best thing to do is meet the curriculum. Okay. All right, so what we're going to focus our attention on now is your notes. All right. So we're going to look at some notes, and then we're going to do some practice. All right, so there are 3 acid and base definitions. The first one is arrhenius. And arrhenius is an acid, a substance that contains hydrogen and ionizes in aqueous solution to produce hydrogen ions. A base is a substance that contains hydroxide ions and dissociates to form hydroxide ions. Definitely 2 vocabulary words from last chapter is the word ionizes and the word dissociates. You might want to pick those up. Those are how they go into solution. Remember, ionize means that it was neutral and formed ions. Dissociate means it was already ions and just simply broke apart. I thought you laughed at that. Okay, oh, I gotta get it right. Get over ambitious. I want to make sure you understand what I have up here as some examples. Up here, do you see this HA? What is the number one thing that lets us know something's an acid? Is you guys have learned, for the most part, they start with the element hydrogen. So we have the element hydrogen bonded to something that we're going to call an acid, whatever that will be. So the A is generic. We know that when you put something in a solution, it likes to form electrolytes, and it does that by forming ions. So the two ions we're going to get is the hydrogen is going to turn into H+, and the acid is going to be your negative component, your anion, whatever that might be. Where you have your base, you've got B standing for your generic substance that's causing it to be a base, which is typically some metal, bonded to the polyatomic ion hydroxide. When it's put into water and it's dissolved, you will get the base, and that'll be your cation, and you'll get the corresponding hydroxide ion. From a very simplistic, which I think your picture still printed out pretty decently, even though it was in black and white, the acid goes into water and you get protons. Your base goes into water and you get hydroxides. And that, on all intents and purposes, is the Arrhenius definition of an acid and base. Now we do need to add something. So over here off to the side, I did add something. This is where the generic definition for neutralization comes from. You guys should have learned back when we did our acid and base, when we did our equations, we had double displacement reactions. So one of a specific form of a double displacement reaction was a neutralization reaction. Is that correct? All right, so we have an acid reacting with a base. How do I know this guy is an acid? Because it starts with hydrogen. How do I know this one's a base? It ends with hydroxide. We know the products are neutral. What are the two neutral products that we get? The one neutral product is water, all right? The other neutral product is the salt. Where do they come from, or how do they happen? Well, you think about it. This guy's going to give us H, and this guy's going to give us OH. Well, what is H and OH going to make? It's going to make water. You take the cation and the anion that's left over, and that's going to give us salt. Now, why did I pick this particular reaction? Well, what is the most common salt out there? NaCl. It is the most abundant salt that we have on the Earth's crust, and it's very, very abundant. If you actually take geology, you'll discover that a good chunk of the Earth's crust contains salt. It's not the most dominant one, but it's in there. It's got quite a bit of it. The largest salt mine in the world is actually in Lake Erie. Okay? So just so you guys know, salt's very dominant. And that's one of the reactions in which we can actually produce table salt. If you cleaned it up, would you actually be able to eat that salt? And would you be able to drink that water? Technically, the answer to both those questions is yes. As long as all your acid and base had actually reacted. You don't need them left over. Okay? So you can take two things individually by themselves. Hydrochloric acid is one of those DEF products that he was talking about earlier in the video. And sodium hydroxide is strong enough to actually kill you. And it produces two things that are highly edible. Think about that. That's pretty amazing in and of itself. Okay? But the reason I'm bringing this up is one of the ways we identify Arrhenius is the actual double replacement reaction we know as neutralization. And often we label it acid, base, water, salt. This guy being my proton producer and this one being my hydroxide producer, giving me pure water in here. Okay? So that's how they look when they come together. And I just wanted to point that out. So that's also part of Arrhenius. All right, moving on then to the next definition is the Bronston-Lowry. The Bronston-Lowry is a very simplistic definition. Its definition is simply proton donor versus proton acceptor. I mean, you don't have a lot to write there for its definitions. What is actually more significant is that conjugate acid-base pair, which I'll give you a chance to write down and then I'll talk. All right. know some of you are still finishing up, but I want you guys to really keep this in mind. It's actually a very simple concept about this conjugate acid and base pair. Keep in mind, notice in the middle of these reactions, you will almost always see this double arrow. What's it mean if there's a double arrow? What's that actually tell you? It could go either way. Well, let's talk about something that's usually common sense. If there's an acid and base going forward, and the reaction will reverse itself, then technically, shouldn't there be an acid and base going backwards? Well, acids and bases are what? They are opposites. So if you're an acid going forward, what should you be going backwards? You should be a base. And if you're a base in the forward reaction, what should you be in the reverse reaction? An acid. But the real acid and base are the ones that are present in the forward reaction. The reverse ones, then, we call the conjugates. Okay? But just keep in mind, you're always a partner. So if you're an acid going in one direction, you better be a base going in the opposite. Now, how do they get this concept of a proton donor and a proton acceptor? Well, this is an organic acid. In organic acids, the hydrogen is not in the front. The hydrogen's always in the back. But it's still a single hydrogen. There's this hydrogen. He's present, right? What do you notice when you get to the other side? He's what? Not present. So how did it happen? He got rid of it. He donated it. Where did it go? Well, water started off with how many hydrogens? How many hydrogens does hydrogen now have? So this was your proton donor, and this one had to be your proton acceptor. So the donor is your acid, the acceptor is your base, and their partners are the conjugate base and conjugate acid. This is actually one of the things you have to do on your test on Friday, your quiz on Friday. You have to tell me who's the acid, who's the base, and who's the conjugate pair on the other, who's their conjugate pair on the other side. All right? We're going to do some practice problems with this in just a few minutes, so don't panic. I have some for you. So, but I do want to start that. That's exactly one of the things you have to do on your quiz on Friday. All right, flipping over to the back. So what I just put a little side note in at the top about hydronium. Here's this polyatomic ion that I made you memorize back in September, or maybe it was October, I don't know when it was, but it was pretty out early in the year. And you've never seen his pretty face ever show up again, other than I had him on the list to memorize. The only thing you guys can even probably remember is he sounds like ammonium. Well, that's because hydronium and ammonium are the only two positive ions that you have. One makes them positive, they don't pick up an extra proton. One is NH4 and the other one is H3O. Ammonia with an extra proton is ammonia, and water with an extra proton is hydronium. All right? Now, I just wanted to put that out there because I wanted you to understand that rarely do you actually have a free floating proton. Free radicals really don't exist in our everyday lives. That's what they're called. When an element is floating around as an ion, it's known as a free radical. Free radicals are really actually not a good thing. They typically are cancer causing. So we really don't want them. So we want our free radicals to bond with something, okay? And that proton will bond itself to water, forming ion hydronium. So we're not looking at the proton count, we're really looking at the hydronium count. But keep in mind, for every proton you get a hydronium, and every time you have a hydronium, you have to have a proton. So they two go hand in hand, they're not separate. All right, so I just wanted to talk about that real quick. So then what is the last definition? The last definition is Lewis. Now, you should recognize the name Lewis by now in some things. Oh, and guess what? Every time the word Lewis pops up, what do you get to draw? So if you didn't like Lewis dot structures the first time we did them, you didn't like them the second time we did them, you're getting an opportunity now to like them because this is going to be the third time you get to do that one. All right, so Lewis dot structures come back into play. Now, what is the definition of Lewis's acids and bases? Well, he says, I don't know why we're dealing with protons, because in a chemical reaction, do protons actually move? I mean, in a sense, can anybody actually lose a proton or gain a proton? If you lose or gain a proton, don't you change your identity? Okay, so we can't really do that. So according to Lewis, he goes, this is ridiculous. All chemical reactions occur really by what the electrons are doing, not what the protons are doing. So shouldn't we have an electron definition? So he came up with one. Well, remember, electrons do the exact opposite of proton. So if according to Bronson, you're a proton donor, you would now have to be electron acceptors, because that's the opposite, is that correct? And if you were proton acceptors, now you'd have to be electron donors, because protons and electrons are going to do the exact opposite. So how do we determine what's going on? Well, ladies and gentlemen, what did he draw? He drew himself some Lewis structures. So what he did is he did the central atom for nitrogen. Remember, nitrogen would have 5 dots, 2 paired, 3 singles, and hydrogen bonds with each one of those 3 singles, making us ammonia. Boron trifluoride. Well, boron only has 3 electrons. Those 3 electrons can be bonded to these fluorines. Now, I want to say this picture's got a fault in it. What should be going around each one of these fluorines that you are not seeing? They should have each one with 6 more valence electrons. Is that correct? The reason why they don't is Lewis isn't concerned about what the fluorines are doing. Are the fluorines important to him? What's important is what's going on between the nitrogen and the boron. If you look at nitrogen, he has his octet, 2, 4, 6, 8. Is that correct? But does boron have his octet? So could this pair of electrons be shared with boron and allow boron to have an octet, causing nitrogen to be the electron pair donor and boron to be the electron pair acceptor? So boron trifluoride is acting as the acid, and ammonia is acting as the base, right? And then you draw your Pinus-Lewis-Dot structure. And technically, 6 electrons, 6 electrons, and 6 electrons should be around this point, just as an FYI. Okay? So when you do Lewis definitions, what are you going to be drawing? You're going to be drawing the dot structure, just in case you were curious. All right. We have a little summative thing here we're going to be doing here at the bottom. You do not have to write anything in here. I think I was nice enough. I condensed the 3 definitions for you. And if you didn't like that condensation, I gave you a different one, showing you the most simplistic to the most complex. But remember, all 3 definitions are true. This one incorporates is the most complex, so it allows more things in. This one's the middle one, and this one's the most simplistic, so it has the least number of members of its acids and bases. All right, so like if you counted all the things that could be an acid and base, Arrhenius is the most restrictive, and Lewis is the most encompassing. But then this is the most simplistic definition, and this is the most complex definition. So yes.
So if I choose Lewis every time, right every time.
That is true, but typically what I'm looking for, but I will tell you, you're absolutely correct on that. But I will tell you, there is a difference. If you're just talking protons and hydroxide, then we are talking Arrhenius. If they mention the word proton anywhere, then they are referring to Bronson. And then Lewis is the one that allows something like, think about it, boron trifluoride even have a hydrogen in it, but it's allowed to be an acid. So it allows things that are not traditionally acids to be acids, vice versa, the same goes with bases. Because traditionally, in the first 2, pretty much you have, for the most part, you either have hydrogen or hydroxide present, or somewhere like, and the thing is interesting, like with ammonia, ammonia does not have hydroxide present, but guess what it does when it goes into water? It forms ammonium hydroxide, so it still has hydroxide present. But where you get to Lewis doesn't make us have to have hydroxide at all, nor does it make us have to have the proton at all. Does that answer your question a little bit? Okay, just watch on that. All right. Properties of acids and bases. I did not make you write anything in here. Now, I want to just go over these real quick. One of the main characteristics is it tastes sour. This is why most of your foods are acidic in nature. Think about it. How many recipes call you to add vinegar to it, or lemon juice to it, or orange juice to it? You think about it. You add lime. You add a lot of that stuff to a lot of your recipes because it's acidic. Believe it or not, we like the taste of sour. And typically we balance it then with sweet. So if something requires vinegar, you typically have to add some kind of sugar or honey to it. And then everybody likes some form of sweet and sour. And think about it, candy. And I don't know how many, but I've always loved the fact that sometimes people love like Sour Patch Kids. You guys like them, okay? Because you like sour. pH is normally less than 7. Well, it has to be less than 7, not normally. Indicators. Now, I just put 2 random Kindred indicators up there. I put litmus up there and I put methyl orange up there. You've worked with others. We worked with phenolphthalein in here. We worked with universal indicator in here. There's a ton of indicators. I just put some examples of indicators. What do acids and bases do? They make indicators change colors. That's what they do. Acids neutralize bases. Now, this next bullet, nobody should miss this. Because it was one of the very first labs we really did in here, is you put zinc and hydrochloric acid, and we produced hydrogen gas and barked the test tube. And what are acids known to do with metals? Anytime you take an acid and react it with a metal, you produce hydrogen gas. And anytime you do that, you bark the test tube. And I believe you barked the test tube about 3 times throughout the year this year. Is that correct? So that particular experiment, we've done a lot. Another one, if there is carbonates present, like baking soda. We've done baking soda a lot in here. The gas that's always produced is carbon dioxide. So anytime an acid reacts with a carbonate, not only do you get the water and the salt, but you also get the CO2. All right? And then remember the proton donors. And I just want to remind you that even though you get this proton, it's H+, it really is going to show up in solution, not as H+, it's going to show up as hydrogen. So I added that to the bottom of your notes. All right? All right, and then we're going to move over to properties of bases. And properties of bases, well, they tend to release hydroxide. They neutralize acids. By the way, what's the number one thing? Does anybody know? You guys have them all the time. Anybody ever take them? Anybody ever have acid reflux? What do you take for acid reflux? Well, a lot of people use Tums. You can use Balox. All right, you can do Rolaids. Is that correct? Well, they're called antacids for a reason. All right? Well, all they are is bases. And by the way, if you're at home and you're in a pinch, baking soda will do the same thing. It just tastes like garbage when it goes down.
And don't put too much.
No, just a little bit, but it will work. All right? They denature proteins. Again, bases turn indicators colors. That's all you need to know. And why do we typically not eat bases? It tastes bitter. By the way, if you ever want to try it, take your finger and put your finger in some pure cocoa. Like, and taste it. It is nasty. If you don't believe me on that one, try a little bit of real vanilla. Oh, tastes nice. Okay, all right. What else is it? By the way, have you ever had a Tums that wasn't flavored? They're gross as it is. But try an unflavored one. Good. They're literally like putting chalk in your mouth. Okay? Anybody ever have a bad cup of coffee? Okay, you do not have to tell me if your parents ever did this to you or not. Maybe you just did it by accident. You get soap in your mouth. Now, this just happened to happen to you in the shower. We're just going to assume that it wasn't because your parents were mad at you and stuck out a toothbrush. But I will tell you, my kids knew that they're not that toothbrush, you better watch the toothbrush, because I'll go to still go to toothbrush. I was a bit all right. Anyway, so those are some things to think about. All right, stopping here for just a second. This is a good place to stop. Put the lights on so some of you can wake up. And I want to stop and just look at some practice things with these 3 theories. Okay? All right, if the person next to you falls asleep because the lights were off too long, wake them up. Because at least then they can understand the homework. Now, what I'm going to do for you on the homework is I thought I would do the first one in each section with you, And then I'm gonna leave you the rest of them to try on your own. That's my intent. Okay. All right, so let's look at question number one. Question number one is Arrhenius. Now, instead of looking at Arrhenius as this guy makes protons or this guy makes hydroxide, we are looking at this one from the neutralization reaction perspective. So you're going to have to tell me who's the acid, who's the base, who's the salt, and who is water. So on question number one, what is H2CO3? That's my acid. Now, you can either write the word acid out, or you can just label it A. I'm not picky because it's the only one with an A, okay? What is NH4OH?
Base.
It is my base. What is ammonium carbonate? Ammonium carbonate. It is the salt. And what is H2O?
That's water.
That's your water. So you have an acid and a base, and then what do you know about these two? These two are what? Neutral. Now, I do have to tell you something at this point in time, which we're not going to quite have time to get into. There is sometimes my salt can be slightly acidic or slightly basic. My water will always be neutral. We are making an assumption that the acid and base are of equal strength. If two things are of equal strength, then are they going to truly cancel each other out?
Yes.
But could you put a strong acid with a weak base? If you take a strong acid and put it with a weak base, the resulting salt is not going to be neutral. That resulting salt is going to be slightly acidic. Or if you have a strong base and a weak acid, then it would be slightly basic. Because you would not completely neutralize everything. It wouldn't do 100% neutralization. That is known as hydrolysis. We are not going to 100% get in there, but I do not want to leave you misleading. I want to let you know that we can have salts that are slightly acidic or slightly basic, but we still refer to them as being neutral in general. But I do need to let you know that sometimes does happen. All right, and that process is called hydrolysis. So you've got 3 of these then to try on your own, labeling acid, base, salt, or water. On the bottom, there is some Bronston-Lowry ones. Now remember Bronston-Lowry. We have to remember the definition. We're looking for the proton donor for my acid. We're looking for the proton acceptor to be my base. The counterpart on the other side, one's an acid, the other one's going to be the conjugate base, and if one's the base, and its partner is going to be the conjugate acid. So now, looking at my first reaction, we have NH3. I just want you to tell me, when you move to the other side, what happened to NH3? It gained a hydrogen. Does everybody see that? It went from NH3 to NH4. What happened to water as it went to the other side? Okay, so which one is the proton donor? The one that picks it up or the one that loses? The one that loses. So the proton donor has to be the acid, and its partner on the other side then must be its conjugate base. The one that picks up a proton must be the base, and its partner is the conjugate acid. So that tells me these two go together, and if you want to look at it, these two go together, all right? I did not make you draw in those brackets when you take the test. I just did that for visuals to help you out on the homework, all right? I do want to let you know on a test or quiz, I do not make you draw those brackets I just drew in. I'm drawing those brackets in right now so you can see which ones were partners. Always keep in mind, if you're acid going forwards, then what better you be going backwards? Base. And if you're base going forwards, what do you have to be going backwards? Because acids and bases are what? They are opposites. Okay, good job. All right, now, which one's the most complicated? The one that's most complicated is the Lewis one. Now, the first thing we're going to do in this Lewis one is, I'm going to turn the lights off so you can see my drawing a little bit better. Second thing I want to let you know, there is a mistake on the key. There should be no blank on the product. So you can go through, in any place through the product, you can put an X. We are only needing to know who is the acid and who is the base. The product is just a species that is formed from a Lewis acid-base reaction. So what do we have to do? I already told you what you have to do. What's the first thing you have to do if it's a Lewis acid-base question? You've got to draw the Lewis dot structures. So what does aluminum chloride look like? Now, this is where it's a little bit of a misnomer. You would have learned earlier that this was trigonal planar. And this is what it would have looked like. Yeah, it's amazing. You have to recall stuff I taught you at the beginning of the year. All right, now, on a side note, you do not have to draw this one. This one's part of your notes. You would have drawn this when I taught this earlier. It was trigonal planar. That's because there were no extra electrons around aluminum. Aluminum only had 3 valence electrons. It was going to give those electrons up, and it is going to equally distribute at 120 degrees to each other. For Lewis, we are making octets. Is that correct? So we're making octets, so I need to have all 4 sides accounted for. So when I'm drawing out my Lewis dot structures for the Lewis acid and bases, when I draw this, I want to make it look like it's in 3 spots. And my questions, oh, that's the bad looking chlorine. Okay. All right. I'll see if I can fix it. Can I redeem it? All right. I did redeem it. And why is this important? Because I'm not concerned about what the chlorines are doing. The reason I'm not concerned about what the chlorines are doing is all my chlorines have octets. Is that correct? I am concerned about what the aluminum is doing. How many electrons are going around that aluminum?
None.
Here there is. How many electrons are going around that
What
aluminum?
am I gonna get?
There are 6. How many do we need around that aluminum?
8.
So does it need a pair of electrons? All right. Vincent, you have your hand up. I answered your question.
Just say, basically that's what we have to draw it on.
Here's the answer to the question. Lewis dot structures are part of your final. Does chlorine always come with 7 valence electrons? Let's always draw them so we don't make a stupid mistake on the easy ones. Now, I will tell you, you go off to college, and you're doing the Lewis dot structures, and all you're concerned about is the central atom. Do you have to really give me all the details of the exterior ones? The answer would be no, but I can't be that nice to you right now, because I don't want you to make a careless mistake. It's sort of like always put your keys in the same spot when you go home. So when you go up in the morning, you know you keep
I just leave mine where you want.
all right? Now, let's look at chlorine. Now, be careful. This is not Cl. This is Cl minus. What does it mean to be Cl minus? What does Cl minus do? Cl has how many valence electrons? What does Cl minus have? It 8, because what does it mean to be -1? It gains an electron, is that correct? So what we're doing is we're putting aluminum, and we're putting it with chlorine, who already has 8 valence electrons. These -1. Could chlorine easily take one of this pair of electrons and share it with aluminum? Aluminum being the proton, not the proton, the electron pair acceptor, is that correct? And if you're accepting electrons, what are you? You are an acid. If you're donating electrons, it makes you the base. Now, you do have to finish the drawing off to get full credit. I need to see the aluminum bonded to the chlorine. The chlorine finishes off its 8 electrons and puts a -1 still. This one has the chlorine going around the outside. And according to Vincent, you are correct. Typically, I don't need to show all these, but I want you to show them so you don't make a careless mistake on your final, okay? So let's put them in because they're technically there, all right? And ladies and gentlemen, that's how you do Lewis. All right, I have a question for you. I'm going to go down here and give you a hint on 4. Silver has how many electrons? Well, we'll draw it over here. Silver has how many dots in its valence electrons? How many valence electrons does silver actually have? Does anybody know? He has 1. So then my question to you is, what would Ag plus look like then? No electrons. Exactly right. It's not going to look any different than a proton. So does a silver with a +1 charge look exactly like, from a valence perspective, as hydrogen? So does he have any electrons to donate? So he can only be in one Compare what? Acceptor. But I just wanted to point that out. For whatever reason, when students do this, they always get hydrogen right, but they always seem to get silver wrong. So I didn't want you to get that drawing wrong for your silver. So when you're drawing your silver over here, you don't write any dots. You literally write H+. Do you write anything else for that one? All right. I'm going to give you time in class now. It's 11:29. You've got quite a few minutes. You can actually work on this homework, and there's a good chance because you get the majority of this done before you leave here today. And also, if you have any questions, this is a good time for you to ask me the 3 definitions. This is exactly what your quiz looks like. It's verbatim. I even break it up the exact same thing. I put Arrhenius and Bronson Lowry, and then I put Lewis. I'll give you several of each one to answer, and that's exactly what you do when it comes to answering the homework questions. All right, so go ahead and give these a shot. And what do you guys have, about 7 minutes, 9 minutes? What do you have, is it 38? What time is it? 37? 37. Okay, you have 7 minutes. You can go ahead and quit recording. You're going to miss math again, sweetie? One more real Monday left. Do you have coming up a point? Do you have any finals that day?
The 20th, yes, the 9th, or the Friday,
No.
no.
I got time that better if I try. Do you guys keep that? Okay. Yes. Yeah, okay, so there's lots of pairs. So just one of these pairs for the only. It'll be right. I don't know. I don't even skip one. Stop. It's not bad. See, look at those little dots start to pay off.
Yeah, that's
Not hard. Hey, tomorrow's math, so bring your calculators. Yeah, put stuff with it. And then another distribution. And that's how you do it. Oh, Michelle forgot her laptop. Is it still recording? Stop broadcast? Oh,
Thank you.
I hadn't stopped it yet. I wasn't sure.
Stop.
Just hit stop? Okay.